Muted.
Get started. So for this week, last week we studied how to use differential equation to solve a model, and then but this particular week, this chapter 12 is discussing how to model with systems of differential equations. And then it has graphical solutions for autonomous system of first-order differential equations, and also have four very good examples in the textbook: a competitive Hunter model, Predator and Prey model, two military examples, followed by Euler's method for systems of differential equations. You should pay attention to section 1 and section 5. Especially for section 5, I believe we have a homework specifically using this methodology. So, so for interactive situations occurring in a study of economics, ecology, electrical circuits, mechanical system, and control systems, and so forth, systems of differential equations can help. And then there's one specific simulation methodology called agent-based simulation. It has elements of the systems of differential equations model elements there, which is using differential equations in an agent-based simulation system, which is different from discrete event simulation and different from Monte Carlo simulation that we discussed earlier. We only discussed Monte Carlo distribution, Monte Carlo simulation and discrete event simulation, but we never actually touched upon on this a different methodology called agent-based simulation. Even though in this particular course we don't cover that at all, but I just want to point out that you guys, when you get a chance, it happens that you came up with this term or you do more research on that, you can use this section as some sort of foundation theory that might be helpful. And then so for special systems that involves only two first-order differential equations, you can take a look at its autonomous, look at its trajectory, path, or orbit, look at phase plane, look at rest point, or whether there's an equilibrium point, and whether that equilibrium point is stable, and whether it's asymptotically stable or it's unstable. And then we have we have two examples in the textbook, and one is a linear autonomous system from page 526 and a nonlinear autonomous system on page 527. I'm not going deep in there, and you can review that, but I have some graphics that you can roughly get a sense on what that is. So, so for a competitive Hunter model, so if we have dx over dt equal to 0, that's the trajectory for the x as time goes on. It's a line, and then correspondingly for dy to dt equal to 0 for trout, it also have a line which is happen to be 1x is m over n. So, and then in this particular case, we know that the equilibrium point is at the intersection of those 2 points, which is m over n and a over b. And then the textbook has much detailed explanation. Even though we don't really need to understand too much about this particular methodology, we should look at it in section 5. Look at how Euler's method can be used to obtain approximate solution. And then, if in general, the general idea is as time goes on, whether there's a specific going towards a specific point that has has a stable solution. And then also have an example on the predicate and pre-model have dx over dt. You have this function and dy over dt function, and then you can solve. Essentially, whether you can solve for x and y. And then in the textbooks, this section I don't really see it's not. It's something that you would take a quick look, but it's really not that important in my mind. And then Euler's method for system of differential equations. This is something that we should really dig into there and take a look. What's the basic idea? So hold on, let me pull up the textbook and then we can take a look. So for the page 526 and page 527 example, basically the idea is if you have a initial data point from x0 to y0 as time goes by, looking at whether your function is going to converge at a certain point. For this particular case, as time goes on, you can see that at the end, when t is really big, the x would be converging at 0 and 0. So if you when you get a chance to read this section, you would understand what I meant by saying this. And then similarly for the next example, for a nonlinear equation, you would see a very similar case. In this case, it's not stable. It keeps as time t gets bigger and bigger. You will see that it's just not converging at all. And then if we continue, okay, so it's right here. So suppose that we have two systems of equations, and then the x trajectory of the x is dx over dt has a function of f, txy, and then dy over dt. First order derivative is function given by gt xy. And then, so here is saying that, so what we want to do is we use this method. Essentially, what it did is for system patches together a string of tangent line approximation to each curve xt and yt over an interval of I, which t is between t0 and e. So what we really want to do is we subdivide the whole interval to we first subdivide the interval I for the independent variable t into n equally spaced points, and then t1 is t0 plus delta t, and t2 equals to t1 plus delta t, so on and so forth. And then we can calculate the successive approximation to the solution function, and then x1 would be x0 plus f plus this change delta t, because we know dt dx over dt equals to this function, because we have an initial value of x0 and y0, so that we can calculate x1, y1, and x2, y2 all the way to xn, yn. And then the method for system is just like Euler's method studied in section 11.5, except that we iterate two equations corresponding to a system rather than just one equation. So previous chapter, we only studied one differential equation, but this chapter is a systems of differential equations. Right. So let's look at this particular example using Euler's method for systems, and that's dx over dt is in this function form, and dy over dt is in the second function form. And then we have x0, y0 starting t0 equal to 0 with delta t equal to 0.1. So we can do, what we can do is we have t0 equal to 0, t1 would be t0 plus delta t, using delta t step size being 0.1, and then we can get t2, t3, and x0, y0 is 1, 2. And then you can get the first evaluation x1, x1, y1, and x2, y2 correspondingly, and 2, 3. Right. So, and then Euler's method for system is easy to program on computer, and program generates a table of numerical solutions to the system, starting with the input of t0, x0, and y0 with a specific step size, and then we could plot the points x0 all the way to xn, approximating the solution curve xt in the xt plane. Likewise, we can also plot y0 all the way to yn to yt, and then to try to plot that in the yt plane. So let's say if we quickly look at this trajectory and solution curves, if we take a look at the trajectory, one of the example here, so we're saying that if we start with 1, 2 as an initial value, as time goes on, we can consider t as the time goes on. So all the way at the end, it would be somewhere ending somewhere here 0.5, 0.5, I believe. Yeah. And then here it says if we change the delta t step size, what would happen? It would be closer, and then if we further reducing that, we obtain trajectory displayed in figure 12.29, which is on the next page. And then we can find that very close to being truly periodic. And then that's the idea here for Euler's method. In general, it's straightforward. And then continue to use the two examples that we started in the textbook discussed in the previous section, and then try to use the approximation method to discuss how the approximation would work. That's for this section, and then next section that we want to discuss is nonlinear programming. So for next chapter, chapter 13, it's nonlinear programming, and then remember that in chapter 7 we have linear program, and then later, I believe it's next week, we're going to if it's either next week or the week after, we're going to discuss integer program. But unfortunately, that this textbook doesn't have anything on integer program. That's why we use that supplementary mental text. And it's a PDF textbook. It's much more mathematical, rigorous textbook. So if you are interested in certain aspects of the mathematics, you probably want to read certain sections of that textbook. If you are not, it's probably too much depth in terms of derivation and theorem, etc. And then chapter 13 of this textbook, we have nonlinear program. And let's see what is nonlinear program. So you would say that since you already studied linear program, you would think that as long as either the objective function or the constraint has a nonlinear function, then it is considered to be a nonlinear program. And then what would be a nonlinear function? Nonlinear function can be quadratic function, can be powered by cubic function. It can be absolute value, can be anything as long as it's not linear, right? It can be logarithm. Then you would need to solve the problem. And then earlier we had, I believe, in one of the earlier sections of the textbook, we have an inventory problem that to say that what's the right, how to balance between the cost of delivery and storage. This is something that it can be actually solved using calculus, even just taking the second order derivative. And then I think in the example specifically, we use first order derivative, set it to 0, and then get the optimal solution. And then we can take the second order derivative to test to make sure that the function itself achieves minimum or maximum, given that it's monotonic. Otherwise, you would not be able to achieve minimum or maximum for the particular problem. And then, as we actually discussed a while back, the inventory problem is a common problem for many of the e-commerce or any of the supermarket. They have to consider this, and then apparently there will be more factors that you would consider when you come up with this type of problems, such as transportation cost, such as shortage of lost sales, for example. So that's so. For example, if you only have one unit of a certain product in your system, and then it happens you have one demand, then you don't have any lost sales. But if your demand is 2, 3, 4, 5, or more than 1, then you have a probability that can incur certain lost sale, and then you would have probability to occur a lost sale scenario, so that you have some sort of cost that's associated with those lost sales. So if that's something that if you happen that you would see some sort of inventory problem, you should consider those. In other words, for different system or different specific enterprise or or businesses, maybe you want to consider some of those costs because some others may not be as important as the ones that are more important. And then for this example, so we're trying to maximize R because price is a profit is revenue minus cost, and then cost is defined as 400,000 plus 1950 x1 plus 2250 times x2. I believe that the cost function is should be x1 and x2. The second one should be x2, and then because revenue can be defined as price times P1 times x1 plus P2 x2. That's why this is a nonlinear function, just because P is defined as R minus C, and then that's why if we put P into the okay, P is defined as the following two forms at the bottom. And then if we use P1 times x1, so that we have x1 times 0.1 times x1 squared, and also we would have x1 times x2. And then correspondingly, if we have P2 times x2, we would have a function of x1 times x2 and also x2 squared. That's why this particular revenue function itself would have a nonlinear component there, right? And then if we want to, this function at the top, the objective function, I believe it should be max P, maximize the profit. And then if we use this revenue function minus the cost function, we still have a nonlinear component there. So it's a nonlinear function. In this case, the objective function is nonlinear. And then one of the methods, as we all know, we just take the first order derivative and then set both of the partial first order derivatives to x1 and x2 and set both of the equations to 0, and then you can find x1 being this value and x2 being a certain value. And then we use second order to confirm it is indeed maximum, because second order derivative is 0.1 is less than 0. That's why it is the maximum. And then the gradient method of steepest ascent, I believe we already studied this in the other course. It's math. I couldn't remember. 605. We already studied this. So the basic idea is you find out with the steepest ascent direction, and then try to update your solution based on the gradient that you obtained at the specific point, which is the xk, yk in this case. And then use lambda k to be the direction that you use the partial order derivative to be the direction that you are moving to, and use lambda k to be the step size that you're trying to move. And then we also studied this for linear regression, it's nonlinear least squares, and then we can take partial derivatives on both parameters a and b, get the solution for the minimization problem. So linear regression problem actually needs to solve a nonlinear program. And then for constraint continuous optimization, so minimize this function such that 2x1 plus 4x2 equal to 24. And then why this is the nonlinear, just only because we have x1 in the denominator and also x2 in the denominator, which essentially is x1 powered by -1. That's why it's a nonlinear function. And then one of the methods that that's commonly used is the Lagrangian multiplier. The way that you do it, if you have multiple constraints, you would have multiple multipliers. In this case, we only have one constraint, which is this equality equal to 24. We can use a lambda as the Lagrangian multiplier. And then the way that you can set up is this is the Lagrangian equation, which is equals to the objective function plus lambda, use your constraint. And then your constraint would be, you can see at the bottom of the page, lambda equals to 2x1, lambda times 2x1 plus 4x2 minus 24. And then this is your Lagrangian function. And then what you do with the Lagrangian function is you take the partial derivative of x1, x2, and also your Lagrangian multiplier, lambda, and then set all of them equals 0. You can solve for x1, x2, and lambda, and you find your optimal solution. And continue with this. If you have two constraints, you just need to add extra term that is a new lambda. You can call it lambda 2, for example, and then times the same thing, the transformation of the constraints, and then you can do the partial order derivative for all 4 variables, which would be x1, x2, lambda 1, and lambda 2. So you can set all of the 4 partial order derivatives to 0, and then you can find the optimal solution of x1, x2, lambda 1, and lambda 2. So continue with this example. It's just as I just said, take the partial derivatives and then set them to a value, and then you can find x1 is this, x2 is that, and lambda is 0.3947. Once you have x1 and x2, you can get your objective function being 12.71. And then the solution is the shadow price. The amount of the objective function would change for 1 unit increase in the constraint represented by lambda. Because as we can see that so essentially saying, because it's in this example, if we increase 1 unit in the constraint represented by lambda, what's the change of the objective function? This is essentially telling us that lambda itself is representing the shadow price. And then the textbook has another example, which is how to restructure a water container, maximize this, and with this constraint, and it can be solved to use Lagrangian multipliers as well, and then get this. Correspondingly, we can get h1, h2, and lambda, and the objective function. And then there's another example here. So it's also have similar issue that it's nonlinear in the sense that you have that yield function is a function of p, I believe, and then that's why it would become quadratic function, and the methodology-wise, it's the same. Just try to take the first order derivative. Yeah, this is apparently this is pretty much everything for nonlinear programming. We actually just mainly discussed 3 methodologies. Methodology 1 is just take partial order derivative. Methodology 2, Newton's steepest descent ascent methodology. The gradient method of steepest ascent, and the third methodology is Lagrangian multiplier. By no means that these 3 methodologies will be everything nonlinear programming, but that gives you a flavor of how to solve some of the problems. But And also these three approach are actually most commonly used approach for solving nonlinear programming. So that's pretty much everything for these two chapters. I will continue with the homework solutions, and then you can ask questions after this if you have any. Okay. So it's right that we didn't discuss homework 8, right? I couldn't quite remember, but I think I'm correct. So let's see. Let me also, let's discuss homework 8 first, and then we can see if I published the homework 9. I couldn't remember exactly if I did. So let's see. For homework 8, the first one is really relatively straightforward. So we have engaged in business venture, assume the probability of success is 2 over 5, and then successfully we can make this amount, and if not, we lose this amount. That's why you can just get the expected value of business venture. Okay? It's straightforward. For second one, we're trying to get a decision tree, and then in that, for different scenarios with a corresponding profit, then this is a decision tree, and then you can get the value. Expected profit with coffee would be 1900, and then expected profit with cola would be 3950 for this example. And then this example is very similar, saying that whether you want to own or you want to lease. And then this corresponding cost with certain probability and certain payoff. And then as we can see that expected value of own is around $116,000. And then on the other end, expected of lease is not quite as big as this number. That's why it's better to own instead of lease. Okay, this is an example that last time with this last thing. This is we discussed last week in a office hour regarding this problem. So I don't remember who was. I believe I was. Sorry, I couldn't remember. But the idea is he was asking why, no matter what, you would drill, right? So that actually makes sense. What you said was making sense because no matter what happens, you would drill. This particular problem didn't see that when you hire a geologist or you don't hire a geologist, it's basically free. Whether you hire or you don't hire, you don't have any associated costs. That's why, and also what happens is the problem itself is not setting up to the level that it happens that it would change your decision. That's why it looks surprising, but what your argument was really correct for this particular problem. So basically, if you look at the problem setup and then the solution, hopefully you would be able to understand the expected value of all present or don't present the expected value is around 4 million. And then if you don't drill, it's negative 100,000. The expected value of you would choose to drill, which is 3.15 million. And then on the other branch, if you drill, even if you get an unfavorable report, the expected value is 220,000, and then correspondingly the expected value for this two options would be 2.488 million. And when you hire a geologist, and then on the other end, if you don't hire a geologist, the expected value is 1.7 million. And then at the end, your conclusion is you should hire a geologist with the expected value of 2.488. And next question is asking if you have this payoff matrix, shall all work to answer part A and B. So essentially we get an expected value of different alternatives, and then to compare which one would be bigger. And then we can say that in order to maximize the expected value, we want to choose alternative B. And then as a follow-up, the question says that if there's opportunity loss regret table and compute the expected opportunity loss for each alternative, similarly you can get the average being 127.5 being the minimized regret or loss for alternative B. So based on minimized expected regret, you would choose alternative B as well. So this is a homework solutions for section 8, week 8. So now let's go back. Oh, I forgot to change the date. So let's quickly go through this. Hopefully you would be able to access that now. If not, it should be very soon. So so the first problem was so as we said, we can use the movement diagram to determine whether the following zero-sum games have a pure strategy Nash equilibrium, and then we can see that there's two Nash equilibrium, which is R1C1 and R2C2, because they have the same expected value. And then in both of these positions, a unilateral shift by one player does not result in a more favorable outcome. And then the next question, the same thing. We just move either along the row or along the column, and then we can find that if the bottom right is equilibrium, and this is an example of a dominant strategy for the pitcher. In this scenario, there is no reason for the pitcher to throw anything except to knuckleball. So this is this one, and the next one. This one I think not a lot. I think the majority of you actually got this correctly, which is very nice because you can see that this is a connection between the game theory and the linear programming. And then this is a objective function with those constraints, and then correspondingly for calling will corresponding strategy, and then you can try to solve this problem. You will find that objective function is 0 and 10. Yep. So and we can see that, and also, yeah, that's pretty much it. Actually, that's how to use linear program to solve this problem. And the next question, we are talking about how can we have three alternatives, A, B, C, and a mix of the three alternatives under uncertain conditions of the economy. The payoff is in this function, in this matrix. And then we can also use linear program to maximize the payoff for the investor. So he can choose x1 being the portion to place on alternative A, and x2 being the portion to place in alternative B, and then the rest would be on alternative C. We want to maximize P with P is less than or equal to this, and then all these constraints. And then we can use LP-solve to solve this problem. And the solution is x1 is 0.25 and x2 is 0 and x3 is 0.75 with the profit of this. So you can see that the merit of some of the budget planning problem. We want to consider what alternatives that we want to choose. Since in that nature with a certain payoff, then you can use this similar function here. And the next thing that if we look at the same problem, but from the perspective of the economy, what you can do here, and then you can solve this problem. And then the solution is from the for the economy, we would see that economy plays condition 62% of the time, and condition 20% of the time, and 38% for the condition 3. And then investor will be held to a return of 41.25. This is for this problem. And then minimax and max mean is relatively straightforward. You would be able to see that. For 28, I haven't put. I was planning to use SegPath solution for this problem. I haven't put them in yet. I'm going to share that as well. Tonight I'm going to update this solution so that you can have for 28 as well. And then for 40, it's some discussion, but we can use movement. From the movement diagram, we can see that there is a Nash equilibrium being 2,4 at R2 and C1. If Rose wants a better outcome, we can use table 10.2 to evaluate her choices. It's a possibility of different discussions, such as simultaneous without communication or different with communication, and first moves or threads. So this is just some very good discussion here. You should definitely review that. And then for the next question, so we actually essentially use the this payoff for that is compute the payoff matrix. The payoff matrix for doc is as the following. This is the result. And then from the payoff matrix, we can see that there's an equilibrium point at both shooting short range. So this makes sense in that both stock and be more accurate at short range. However, it produced undesirable results for both men, as they both ended up dead in this. So you can review this, and as I said, I'm going to update this solution for 428, and then you have a complete set tonight. Let's say you have any other questions. Yeah, Sekha was asking, can you resubmit the same document? If yes, you could. If I didn't provide any, updates that I asked you to update the document, then you could just send the same document. Of course, if you have already done some work, if you want to share that, you can put that in as well, and then so that I can get a sense, and then hopefully I can give you some feedback based on your submission for the project proposal. And then last one, you're asking about this particular problem. Hold on. So your question was asking that Sekha was asking about this question 5. They're saying that whether we need to find the XY values not given in terms of T, but you still can solve your problem with a certain.
Dr. Harry, can you hear me?
Yes, I can.
Yeah. So actually, my question was in the previous problems. The problem 1, 2, 4. We were given x and y values. There functions actually in terms of t, but for 5th and 6th problem onwards, we don't have that. So how can we, estimate the behavior of those coordinates at, for t tends to infinity value? So that's the reason, I'm just kind of confused there. If we have to integrate the dx dt to obtain the x in terms of, something like 2yt plus c, or if there is any other problem which, concept which I'm missing, then maybe I have to go through the material. But
so the basic idea is if you can find a stable function of some sort of relationship between x and y. For example, in the particular example we saw, if x squared plus y squared is circle, for example, right? As time t changes, if x1 plus y squared, x squared plus y squared equals to a constant, then we know it's irrelevant to t. Then we pretty much know that it would have a stable solution, right? But for this example, I have to think it through. I on top of my head, I don't know how to answer it.
no problem. Thank you.
Yeah. Okay. Okay. I'll take a look and hopefully I can help you on this. Okay. So that's pretty much everything that I planned for this week. And then just remember to submit your project proposal in the Blackboard system. And then let's quickly take a look at the plan for the rest of the semester. So basically, you would have homework 10 and 11 for this week and next week. And then you have, you would have 11 and 12 that's due this week and next. And then next week we talk about graph of functions, the models, and also integer programming that covers pretty much everything. I mean, 2 weeks from today. And then you have homework 13 and homework 14. But homework 14 is really something that you just need to review some of the material. You don't have solution basically is already given. So you only have 3 more homeworks, which would be 11, 12, and 13 for the next 3 weeks. And then hopefully starting from week 13, you would have more time to focus on your project. And then from week 13 all the way to week 16, around 6 weeks, around 3 weeks, around 4 weeks actually, 13, 14, 15, and 16, and then you would be mainly working on your project. And then depending on the timing, we would potentially would be having the project presentation on the 18th, even though that's not final yet. We could be delaying by 1 week, which would be the 25th, and then potentially correspondingly your final report will be due in the week of 25th as well, which essentially by the end of the month of May. So that's pretty much of the plan. So let me know if you have any questions or comments. Meanwhile, I know that you guys are discussing some of the problems in the question. I will go through this again, and hopefully I can provide some insights for some of the questions that you guys are asking. I know that some of them already answered by some of your fellow students. That's great. If you guys have some thoughts on there, feel free to comment to some of the problems. I will comment as well. Okay, that's pretty much everything, and you all have on page. So Mohammed have a question here. Page 481. Page 481. That's for last week, right? I believe so. It's probably, I remember that somewhere textbook has an error there. Yeah, April 22nd, I believe. '22nd. Yeah, I think it happens that we, if we have a spring break, then we would delay the whole thing. So either way, we could discuss when it comes in, which would be this week, week 12, which would be next week. I'll send you an email regarding this. I'm not sure if we want to delay 1 week, that's fine too, if time permits. I'll take a look at the school calendar to see when potentially when is the end of the semester, May 20th, or this week or the week after. If it's a week after, we could just move everything 1 more week. Let me see. If there's a calendar here. No? Okay, thank you. Okay, so we could, yeah, let's do this. So next week, I'll send you an announcement as well. Let's move this to one more week so that this homework 12 will be due instead of 24th. It will be due by the May the 1st. But the week, 2 weeks from now, we still have the regular session to cover those 2 weeks material. And then correspondingly, all the homework after 12 would shift by 1 week. So we could have the final week would be final due would be the end of instead of 22nd, it would be a 28th or 29th. Okay, so that's pretty much everything for today, and then that's it. Thank you.